This might be a logic puzzle that could fry everyone's CPUs. Imagine you and 99 other prisoners are confined to death row. Each prisoner is assigned a number from 1 to 100. Then, the warden decides to conduct a game. If you can successfully pass the game, you'll regain your freedom. Otherwise, you'll be executed. The rules of the game are as follows. There is a closed room with 100 boxes inside. Inside the boxes, the numbers of the 100 prisoners are randomly placed. The prisoners will enter the room one by one. Each person can open a maximum of 50 boxes. If a prisoner finds their own number, they are considered successful. Once the game begins, no one is allowed to communicate, nor can they leave any marks behind. If even one person fails, everyone will be executed. At this point, you're surely thinking, although one person randomly opening 50 boxes has a success rate of 50%, in the case of 100 consecutive attempts, the overall probability of success is only 1/2 raised to the power of 100. Clearly, this appears to be a doomed situation. So is there any way to improve the survival probability? Actually, the key to this problem is not about deciding in advance which box to open, but rather determining the next action from the information already obtained. At this point, a smart prisoner discovered by using a simple loop from mathematics that when you open a box, you use the number inside to locate the next box until you find the box with your own number. See? This significantly increases the overall probability of success, which was almost 0. And how exactly is this achieved? Suppose you are prisoner 50. When you open box number 50, if the number inside is 99, then you proceed to open box number 99 and continue searching for the box corresponding to the number, and so forth until you either find your own number or exhaust all 50 attempts. At this point, you will notice that all the slips of paper inside the boxes will form several closed loops. For example, from box 1 to box 7 and back to box 1. This is a loop with a length of 2. As long as the length of each loop does not exceed 50, then all prisoners will be able to find their own numbers. And through mathematical proof, when the number of boxes is 100, the overall probability of success is close to 31%. The reason for the significant increase in probability lies in how this strategy transforms originally independent random events into an overall probability problem. Although each prisoner's individual success rate was originally 50%, because they were independent events, it resulted in an extremely low overall probability of success. However, the loop strategy binds their fates together. Given this, how does this strategy significantly improve the success rate? Suppose the 100 boxes form a single large loop of length 100. At this point, each loop would require opening all 100 boxes to find their own number. However, the rules only allow opening 50 boxes, resulting in everyone failing. But through mathematical proof, the probability of n elements forming a loop of length n is 1n. That is, when n equals 100, this probability is 1. However, the failure probability of the loop strategy is the sum of the probabilities of all possible loops exceeding 50. Therefore, after calculating with the above formula, it can be concluded that the probability of prisoners regaining their freedom is 0.31. And what is even more remarkable is that even if the number of prisoners is increased to 1,000 or even higher, their overall success rate can still exceed 30%. This puzzle also reveals a profound insight, namely, in certain special circumstances, an individual's optimal choice does not lead to the optimal outcome for the group. If each prisoner acts independently, although each individual's success rate may seem relatively high, the overall result is nearly 0. However, by cooperating and forming a unified strategy, it is possible to achieve results far beyond expectations. Mathematics is not merely dull formulas. It is more like a powerful tool for thinking, one that helps us find solutions in dire situations, whether it is the prisoner box problem or the various challenges in real life. As long as we are skilled at using mathematical thinking, we can turn seemingly impossible things into possible ones. And you, the one in front of the screen, has your CPU overheated yet?